So we're going to talk about kinematics today. We are actually going to figure out what the four kinematics equations are so that we can use them in future problems. Basically, kinematic equations can be used to relate velocity, acceleration, time, displacement, all those quantities that we've learned about together. So it is a slightly more algebraic way to solve problems rather than solving everything either using logic or using graphs. So it can save you a little bit of time sometimes. But of course, instead of just throwing equations at you, I kind of want to show you where they come from so that it makes sense. So we're going to be talking about kinematic equations. Okay, so there are a total of 4 kinematic equations. So the first 2, you can actually figure out what those ones are by looking at a velocity versus time graph for accelerated motion. So I'm just going to draw a basic velocity versus time graph. I'm not even going to add numbers to it. I'm just going to draw the basic shape of a graph. Looks something like this. Okay, so we know a couple of things already about this graph just because of what we've learned about so far this school year. So first of all, if we know that the velocity is increasing at a constant rate, like it is in this graph, then we know the slope of this line is equal to the acceleration. So slope equals acceleration. And of course, acceleration has the symbol, sorry about the bell, lowercase a. Also, you'll notice with this graph, and I just did this so that this can work for any velocity versus time graph, this one in particular also has a y-intercept. So the intercept, because this is a velocity versus time graph, the intercept is just telling us the initial velocity. So make sure that makes sense. Pause the video, think about it for a minute. Make sure that makes sense to you. So the initial velocity has the symbol v, but with a little 0 after it. So we say v naught when we're talking about that. So initial velocity or v naught. Okay, so now that I've defined those two things from my graph, if I'm trying to write just the general equation for a graph, so y equals mx plus b, you'll notice for this graph, I don't have y and x. I have v and I have t. So I can go ahead and substitute some of these quantities in the y equals mx plus b equation with the variables that are actually on my graph. So y is actually velocity. M, that is the slope, in this case the acceleration. Instead of x, we actually have time. And b is the y-intercept, so in this case, v initial. So simply by writing the equation of the line, we have actually come up with our first kinematic equation. So I'm actually going to take this kinematic equation, and I am just going to scooch it up here so we can put them all together. So that is what that is. Actually, you know what? No. You know what I'm going to do instead? I am actually going to start a new table because that's going to be too difficult. So why don't I start a new table with all of the kinematic equations? So kinematic equations. Oops. So the first kinematic equation, and you should make a list of these in your notes. These are going to be basically solid gold for the next 2 chapters for you guys. So the first one is v equals a times t plus v naught. Okay? Like I said before, there are 4, so I'm going to leave spaces for those and I'll just come back as we derive them. Okay, so the second kinematic equation actually can also be found from a velocity versus time graph. So why don't I go ahead and erase some of this stuff so that we can just use the same graph. See ya. Okay, so when I am looking at this graph, I also know about this graph that if I were to find the area underneath the curve of this graph, so if like I was going all the way out to this time here, and if I were to find the area underneath this whole thing, so I'm actually going to highlight. So like this whole area under here, I know that this area is actually equal to the displacement of my object. Remember, when you have a velocity versus time graph, finding the area under the line gives you the displacement. So I'm going to go ahead and write that in, the displacement. Also, remember that this point here, where the blue line starts, that is our y-intercept, so that is v initial. Okay? Now, when I'm finding the area underneath this line, because of the shape it makes, it's easier to break it apart into two sections, kind of like this, where it is a triangle on top of a rectangle, because it's much easier to find the area of a rectangle and the area of a triangle and then just add them together. So to find the area of the rectangle underneath, because it's a rectangle, area is just going to be found by multiplying the base and the height. The base of the rectangle is just t, so time. And the height of the rectangle is your initial velocity. To find the area of the triangle above, remember the equation to find the area of a triangle is 1/2 base times height. So 1/2, the base is just t, and then the height is actually this height between these two variables right here. So it's not the entire height all the way up to v, it's only the difference between v naught and v. So v minus v naught. Okay? So to find the area, it would be base times height for the bottom triangle plus 1/2 base times height for the rectangle that's sitting on top of it. I know the area is displacement. Base times height is VOT, or V naught T. And the other shape is going to be V minus V naught times time. Now, you could leave it this way, but actually it is more useful to use the first equation to help simplify this down a little bit. So I know that the first kinematic equation is V equals AT plus V naught. So I actually can do a little bit of algebra here. If I subtract V naught from both sides, you get this. And if I plug in A times time for this quantity here, it actually simplifies it down quite a bit. So what you end up getting is delta x equals V naught times time plus 1/2 AT times t. So essentially that comes down to A times t squared. Okay, so that is the second kinematic equation. So let me write that down in my little table here. So delta x, displacement, equals V naught times time plus 1/2 acceleration times time squared. And that's just a little bit more simplified, easier to use. So that's always how the second equation is going to appear. No matter where you're looking it up, that's always what it is. Okay, so for the third equation, we're not going to use that graph anymore. We are actually going to move on to thinking about how to calculate the average velocity. So when you are finding the average velocity for constant accelerated motion, so something that is accelerating at a constant rate, there are actually two ways to find the average velocity. The first way is to take the displacement of the object and divide it by the time. And the second way, if you're moving at a constant acceleration, you can actually just take the straight average. So V average equals V initial plus V final over 2. So you add them together and divide by 2. That actually does tell you the average velocity. So if I take these two equations, both of them are equal to V average, so I can actually just set them equal to each other. Like this. Now, what I actually want to do next is multiply both sides by t so that I'm solving this equation for displacement. So what you end up getting is that. Now, this is the third kinematic equation. Sometimes when you look up this equation, or when you look up the kinematic equations, like if you were to just Google kinematic equations and get them, sometimes this one is written this way instead, and it just means the same thing. But the 2 in the denominator is just pulled out as a 1/2 in the front. So it's the same thing. Sometimes you see it written one way, sometimes you see it written the other way. It's honestly just a matter of personal preference. I actually do prefer the second way, so that's how I'm going to put it in the list because it takes up less space and it's easier to write. So this is the third kinematic equation. So going back to my list, let me copy that in. Displacement equals 1/2 V initial plus V final, which is just V, times time. All right, so we've gotten 3 out of our 4 kinematic equations. Now we just need to do the fourth one. Now, the fourth kinematic equation is actually just a little bit of algebra. So what I can do is I can take 2 of these equations, and hold on, let me set up my spot for it. Move down. I'm going to take 2 of these equations that I just found. So I'm going to take this one here, and I'm also going to take the first equation. So I'm going to take both of those and move them down to the bottom real fast. So let me copy them. So that was the first one. And this is the second one. All right, so what I'm going to do first, basically I need to figure out a way to combine these 2 equations. One way that you could do that is take the second equation and rearrange it for time. So when you do that, I'm going to subtract V naught from both sides and divide both sides by acceleration, and you get this. I can actually take this quantity and plug it in right here. I know this looks crazy, but really from this point on, all we're going to be doing is simplifying this down. So what I'm going to do first is multiply both sides by 2 to get rid of the 1/2. And I'm going to multiply both sides by a to get rid of the fraction in the second parentheses. So 2 times a times displacement equals V plus V naught, V minus V naught. Okay? So what I'm going to do now is FOIL out the right side. So you get V squared plus v naught minus v naught minus v naught squared. So you get this quantity right here. All right, so these two terms right here cancel out, which is kind of nice. Don't you guys love algebra so much? And then what I can do is add v naught to both sides. So this is solved for velocity squared. So velocity squared equals, I'm going to move it to the other side because usually the one that's isolated is on the left-hand side, equals 2 times, oops, I'm actually going to flip this because this is how it usually appears. Doesn't really matter what order these terms go in. V naught squared plus 2a delta x. So that is the fourth kinematic equation. So it took a little work to get there. Luckily, I'm not ever going to ask you to rederive these. I just wanted to make sure you saw that these four equations didn't come from nowhere. I'm not just pulling out random equations and saying, trust me, it's true. Like, you can actually see mathematically, they all kind of come from things we've already learned and from algebra. So let's go ahead and copy that fourth equation in our little table up here. So v squared equals v naught squared plus 2a delta x. So those are our four kinematic equations. So let me kind of clean this up a little bit. What I'm actually going to do is show you now how to use them. So I'm going to do one sample problem so that you can get started on the assignment. So let's take this whole box and move it down to a clean space on my notes. Okay, so moving down. And actually, I'm going to do one thing. So I'm going to add a little bit to this. So I have my four kinematic equations. One thing that can be very useful when you are solving these types of problems that use kinematic equations is realizing that there are a total of 5 variables in these equations. So in these equations, if you look at them carefully, there are 5 variables that appear. There's velocity initial, so v naught, acceleration, time, and displacement. So we have a total of 5 variables that appear in all 4 of these equations, and we have 4 equations. Each of these kinematic equations, what makes this list very nice is that every single one of these equations eliminates one of the 5 variables. So when you are doing a problem, if there is a variable that you do not know the value of because it's not given to you in the question, and also it's not like the point of the problem, you're not trying to solve for it, you can just carefully choose the equation that does not contain that variable. So what I'm going to do is make off to the side, I'm going to say doesn't contain So the first equation has velocity, acceleration, time, and initial velocity. So it doesn't contain displacement. The second equation has displacement, initial velocity, time, and acceleration, and then time again. So that one does not contain velocity. The third equation does not contain acceleration. And the fourth equation does not contain time. So adding that to your list of kinematic equations can sometimes be useful because it allows you to more quickly figure out which equation makes sense to use for the problem. Okay, so this is going to be my full table. This is my ending result. Okay? Okay. So let me erase this. We can do a problem together so you can see how to use them. So for this problem, let's say, I'm going to keep it kind of simple. A rock slides, try to keep my handwriting nice, on ice, a distance of 39.2 meters for 14.3 seconds before stopping. And I want to know two things. So part A, what is the initial velocity? And then for part B, what is the acceleration? All right, so one thing I didn't mention about these equations, I probably should have, is that all four of these equations do contain V initial, so V naught. Every single one of all four equations have V naught in them. So if you're ever in a situation like this problem where V naught is not given to you, usually that will be the first step. So why don't I add that underneath just like as a little note? All equations contain V naught. Okay, so this question in particular kind of points that out because step one is to figure out what V naught is, and then step two is to figure out the acceleration. So for this problem, probably I'm really concerned with the acceleration, but I know I need to find V naught first before I can find the acceleration. All right, so what you want to do first in a kinematics problem is just go through and highlight all of the numbers that you're given, or write down a list of all the numbers that you're given. So I have 39.2 meters. I have a time, 14.3 seconds. And I'm also told that it comes to a stop, which isn't a number, but it is useful information that I can use. So what I'll do is I'll start my list. I have 5 variables. I have V, V naught, acceleration, time, and displacement. Let's just kind of fill in all of the numbers that I have. I don't like that green. I'm changing it back to white. Doesn't match my aesthetic. Hold on. Better. Okay. So what am I given? So I'm told that it goes a distance of 39.2 meters. So I can use that as the displacement. I'm assuming it's traveling forward. So we'll say positive 39.2 meters. I'm also given the time is 14.3 seconds. I also know that the rock is coming to a complete stop. So my final velocity is going to be 0 meters per second. Remember, V final is usually, it's just written as V. You don't have to worry about the final. Okay, so part 1 of this question is asking us to find out what V initial is. So I'm going to write equals question mark for that. So you can see on my list, the only variable that I either am not given or do not care about is acceleration, at least for part A. So I'm going to use the equation that does not have acceleration, which is the third equation. So let me go ahead and copy that equation down in my aesthetic color. So displacement equals 1/2 V initial plus V final times time. All right, so you can either rearrange this first to solve for V initial, or you can plug numbers in and then rearrange. Of course, I'm a physics teacher, so I like to rearrange first. It's neater. You don't have to worry about writing the numbers every time. It's just easier to write a variable. So the first thing I'm going to do is multiply both sides by 2. Algebra. And next thing I'm going to do is divide both sides by time. And then the final velocity, I could subtract that over to the other side. However, I do know that it's 0, so I'm just going to take this v and just take it out because I do know that it's equal to 0, so I can pretty much ignore it. V naught plus v, because v is 0, is just going to be the same as v naught. So now all I have to do is plug the numbers in, and that will tell me what the initial velocity was. So 2 times 39.2 meters over time, which is 14.3 seconds, equals v naught. So when I multiply 2 by 39.2 and then divide by 14.3, I get 5.48. So remember significant figures, be careful with those. I want to round this to 3 significant figures because that's what my 2 values are. The 2 is an exact number, so you can kind of ignore that. All right, and the unit, because this is a velocity, is going to be meters per second. Okay, so now what I'm going to do is I'm actually going to take that value and put it into my table. So get rid of my question mark because it's not a question mark anymore. Now I know what it is. V initial equals 5.48 meters per second. So I'm done with part A. Now for part B, it says, what is the acceleration? So that's where my question mark is going to go now. Now I actually can use any of the equations that contain A. So basically I can use 1, 2, or 4. It doesn't really make sense to use equation number 3 because it doesn't contain acceleration, so it would not allow me to solve for acceleration. So really you can kind of take your pick, 1, 2, or 4. You will get the same value for acceleration no matter which of those 3 equations you use. So you want to pick the one that just looks like it'll be the easiest to solve algebraically, which for me, I think probably looks like the first equation. The first equation is the easiest, it's the simplest, there's no squares involved, it's just straightforward. We'll use the first equation. So V equals acceleration times time plus V naught. And of course I know that V is 0, so I can do the same thing here that I did before and get rid of it. I want to solve this for acceleration, so the first thing I'll do is subtract V naught from both sides. And then I'll divide both sides by time. Like that. So you get negative V naught over time equals acceleration. I'm going to move that down a little bit. It's bothering me that it's not centered. There. So easy enough, all I have to do is plug my numbers in. So negative 5.48 meters per second over the time, which was 14.3 seconds. When you divide that, you get negative, and again, 3 sig figs, guys, negative 0.383 meters per second squared. So I can go ahead and add that to my list. Aren't these questions fun? I'm the only person that thinks that. Don't worry, I know that. All right, so now you guys have seen me do an example, and this one was actually a good example because I had to solve for V initial first, which is sometimes the case. Sometimes V initial will be given to you. In that case, you can kind of ignore that step, but sometimes you have to find it first, and this is a case where you had to find it first. So go ahead and get started on the practice. The practice is all just algebra problems like this. Make sure you have your kinematics equations handy. So this little list right here, pause the video, write it down if you haven't yet. Other than that, go ahead and get started. You guys are amazing. All right, good luck.